I'm going to try and do it tomorrow and give it to you Thursday.
Thank you.
Okay, so in section 4.1, the exponential functions, remember last class period, we talked about the definition of an exponential function. And so it was this. It was f of x equal b to the x. Okay, so b is your base and x is your exponent. Remember, an exponential function, where's the variable located? In an exponential function, we said the variable is located where? In the exponent. All right, and we also said that the base must be a positive number, and that idea is going to be important when we talk about logarithms as well, because they're connected. Exponentials and logarithms are connected. And so the base must be positive. Now the base must be any positive number except 1. The base cannot equal 1. Because if the base were 1, 1 raised to any power is always 1, and that's no longer exponential, that's linear. Okay. So then I think we graphed one of them. We did. We graphed an exponential function. I want to make sure I don't graph the one that's on the worksheet or the one that we did. So let's see, the one on the worksheet has base 2 and base 1/2. So let's look at this one. Suppose we want to graph f of x equal 3 to the x minus 5. 3 to the x minus 5. Okay, now remember, all exponential functions, and we talked about this, all exponential functions have a horizontal asymptote. So there's a horizontal asymptote. Okay, it's a horizontal asymptote. It has a horizontal asymptote. Do you think you know what the horizontal asymptote is here? Asymptote. Do y'all think you know what the horizontal asymptote is? Okay, it's -5. So the base raised to the exponent and then subtract 5, that -5 is a horizontal asymptote. But remember, it's a horizontal line. How do you name the equation? How do you write the equation of a horizontal line? Is it x equal or y equal? Y equal. So my horizontal asymptote is y equals a -5. That's your horizontal asymptote. Once you find your horizontal asymptote, you graph it, and then all you need are 3 points, and that's it. And it's very simple. Graphing an exponential function is fairly simple. All right. So using graph paper. I think I put some graph paper up here if you need any somewhere up there. Check and see if it's up there. There were a bunch of them. So the first thing you're going to do is you're going to graph the horizontal asymptote. All right, so the horizontal asymptote is what equation? Y equals -5. So we're going to graph y equals -5. So y equals -5 is right here. So when you graph the horizontal asymptote, you're going to use a dotted line. A dotted line to name the horizontal asymptote. Okay, now here's the next question. Do you think the graph is above or below the horizontal asymptote and why? Is this graph going to be above or below the horizontal asymptote and why do you think that? It's going to be above because there's no reflection. Since there's no reflection, now remember, if there was a reflection about the x-axis, you would see a negative out here. Okay, so since there is no reflection about the x-axis, the graph is above the horizontal asymptote. Okay, so since there's no reflection, and we're going to do reflection in a little while, but since there's no reflection, the graph is going to be above the horizontal asymptote. And remember, exponential functions, how an exponential function looks. An exponential function looks like this. It rises rapidly like this, and then it levels off, but still decreasing over here. So see how it rises rapidly? So this is increasing. It could also decrease. So it decreases rapidly, and then it levels off. And all these goes towards the horizontal asymptote. So remember last time we talked about the graph leveling off or going towards the horizontal asymptote. Will it ever cross a horizontal asymptote? Do you remember what we said? It will not. Okay, it will not cross or touch the horizontal asymptote. It'll get close to it, but not touch it. Okay? All right, so over here, here's my horizontal asymptote. My horizontal asymptote is y equals -5. Remember, the horizontal asymptote is always this number right here. This number's -5. That's kind of the same thing like a vertical shift. Remember the vertical shift and the transformations you have to turn in Tuesday? Section 2.5 is due Tuesday. That's on transformations. So remember the vertical shift? Okay, so you shift down 5 units. That's what this is. So that's a vertical shift. So y equals -5, that horizontal asymptote. And my graph is above this horizontal asymptote. And all you do is just use a t-table. Use a t-table. So if x is 0, I get y equals 3 to the 0 minus 5. And what's 3 to the 0? If you don't remember, use your calculator. What's 3 to the 0? 1. 1 minus 5 is a -4. So then you plot the point 0, -4. Watch how simple this is. Right here. You need 2 more points. So what I would do is I would just pick 2 points to the right of 0, the one I just did. So if x is, let's say, 1, if x is 1, I get y equals 3 to the first power minus 5. What's 3 to the first minus 5? Not -2, good. So -2. So I plot the point 1, -2. So that's here. Okay. If x is 2, just go increments of 1. It doesn't matter. 0, 1, 2. If x is 2, I get y equals 3 squared minus 5. What's 3 squared minus 5? That's 9 minus 5, which is 4. So I get the point 24. And so notice, all you do is this. Watch how simple this is. So here's the part that rises rapidly. You see this part? And what happens on this side? It gets closer and closer to the horizontal asymptote without touching it. So do that and you're done. There's your graph. Okay? So that's the graph of f of x equal 3 to the x minus 5. So you first thing you need to do is determine what your horizontal asymptote is. Graph it. And how do you graph the horizontal asymptote? With a dotted line. Since there's no reflection about the x-axis, the graph's going to be above the horizontal asymptote. And just plot 3 points. Connect the dots, and then make sure that on this side, the graph is going towards the horizontal asymptote without touching it. So make it cross. If you make it cross, that's incorrect. It doesn't cross it. It goes towards it without touching it. Okay? Now let's talk about the domain of this. Let's talk about the domain of a horizontal of an exponential function. Remember when we talked about the domain of a quadratic function? All right, before we do that, let's talk about the domain of a quadratic function. Recall what that looks like. Yeah. You all agree the domain of a quadratic function, all quadratic functions is all real numbers? So the domain is -infinity to infinity? Because if you look at the graph, regardless of whether it goes up or down, you're going from -infinity all the way to what? Positive infinity, regardless of whether you're going up or down. So every point on this graph represents any real number for x. Any number for x will be on this graph. Now the range is different though. Remember, the range depends on the vertex and whether it goes up or down. Okay? The same thing applies here. What do you think the domain of, let me find the graph. What do you think the domain of this exponential function is? Our real numbers. Because if you go from left to right, see how this arrow is pointing this way? So if I'm looking at negative 1 million, am I going to get a point on the graph? Yeah, it's going to be way down here towards the close to negative 5. But I'm still going to get a point on the graph. I'm going from negative 5 all the way to what? Where? Keep on going, right? Because at x equals 9 right here, am I going to get a point on the graph? Yeah, it'll be way up there. It's going to be a big number. At 100, I'll get a y value. 1 million, I'll get a y value, and so on. So for any exponential function, what's the domain? Our real numbers. So the domain for an exponential function is our real numbers. And that's true for all of them, right? This is for all. That's for all exponential functions. But the range is not true for all exponential functions. The range depends on the horizontal asymptote and whether the graph is above or below. All right, so let's find the range of this one. Okay, so let's talk about the range. All right, so the range, you go from the negative y-axis to the positive y-axis, correct? Okay, so I start touching the graph. And when I say touching the graph, think about the horizontal asymptote. I start touching the graph because the horizontal asymptote is part of it. I start touching the graph when I get to the horizontal asymptote, right? Okay, now I'm going to ask you this. Is any point on the graph ever going to be a negative 5 before the y value? No. All right, but it gets close to what? Negative 5. So negative 4.9999999 and so on. All right, so I'm going to use negative 5, but I can't use a bracket. I'm going to use a what? Parentheses. So the range is from negative 5 all the way to what? Infinity. Just make sure you understand that it's not a bracket this time because none of these y values on this graph will ever be what? Negative 5. It gets close and close to it, but it's never going to be negative 5. So my range is going to be from negative 5, parentheses, to infinity. Okay? That's your range. All right. Now, let's look at this. And then we're going to come back and compare those two graphs. This graph here, let's look at f of x equals 1/3 to the x minus 5. So what's the difference between that and the previous one we just did? Well, be a little bit more specific. The what is different? The base. The base. No, that's not a coefficient. That's a base. So 3 is the base in the previous one. 1/3 is the base here. Everything else is the same. So my horizontal asymptote is the same. What's a horizontal asymptote? Negative 5. So my horizontal asymptote is, now this will say negative 5. What do you have to say? Y equals. Okay? So then you're going to graph it. So here's y equals negative 5. Right here. Okay. Now, is my graph above or below the horizontal asymptote? It's above because there's no reflection. See, if there was a minus out here, then that would indicate a reflection. Okay, there isn't any, so it's going to be above since there's no reflection. So I'm using a t-table, just like I did before. And what's a nice number to use for x? 0. In fact, when you let x equal 0, what exactly are you finding when you let x equal 0? The y-intercept. Good. You are finding the y-intercept. So if you go back to the previous one, when we let x be 0, we had gotten this point here, 0, -4, remember? So if you look at the graph, 0, -4 is the what? The y-intercept. So an exponential function is always going to have a y-intercept. So to find the y-intercept, you let what? X be 0. So I would let x be 0 because that's going to be my y-intercept. And so when x is 0, I get y equals 1/3 to the 0 minus 5. And what's 1/3 to the 0? 1. And what's 1 minus 5? -4. Okay? So then I plot the point, 0, -4, which is here. Okay? Now give me another number for x. 1. So if x is 1, I get y equals 1/3 to the first power minus 5. Now you may need a calculator for this because you do have a fraction. So you have 1/3 minus 5, which is what mixed number? Use your calculator if you need to. -4 and 2/3. -4 and 2/3 in your calculator. Make sure you got that. So that's -4 and 2/3. So 1, -4 and 2/3. 1, -4 and 2/3 is here. Okay? Now, I know what's happening on this side. What's happening on this side? I can start drawing points on this side. What's happening on this side? It goes towards this side of the x. I keep saying x-axis, but I mean the horizontal axis. See it? All right. So use your knowledge. So that part goes like this. Now remember, it doesn't touch, right? Now I got to figure out what it does here. So let's pick some negative numbers on this side of the y-intercept. So let's pick -1. Now you need your calculator for that because a lot of you don't remember something about negative exponents. All right. So x equals -1. I get y equals 1/3 to the -1 minus 5. Now, without using a calculator, I just want to see how many of you remember this. What's 1/3 to the -1 power? No, it's not 1/3. It's 3. You remember to make that exponent positive, you take the reciprocal of that base. So if you don't remember that, just use your calculator. On your calculator, you got to be careful. You got to put that in parentheses. So on your calculator, you're going to say this. Well, first of all, let me just verify that 1/3 to the negative first power is 3. So you say parentheses, for that parentheses, 1 divided by 3, close parentheses, raised to the -1. So that looks, press equal, and you get 3. All right, so that's 3, but I'm subtracting 5, so what's that? -2. So I get -1, -2. So -1, -2. And give me one more point on this side to make you draw a better graph that's decreasing rapidly right here. So it's decreasing rapidly, but I got to draw a better graph. So let's use -2. Use -2. So if x is -2, I get y equals. Yep, it'll be 9. Huh? I'm sorry, say it again. Yeah, but 1/3 to the negative second power is what number though? 9. Use your calculator if you don't remember it. So 9 minus 5 is a 4. And you're done. You just plot those points and draw your graph. So -2, 4 is here. And that's enough to draw this. And so that's it. There's your graph. Okay? So as you go from left to right, what's your function doing? Your function is doing what? Decreasing. And the previous one, when you go back to the previous one, as you went from left to right, this function is what kind of function? An increasing function. This one here is decreasing. This is decreasing. So y equals 1/3 to the x minus 5 is decreasing. All right, so let's talk about what makes it increase or decrease. You see the base here? This base here? What's this base? 3. This base here is a third, right? This is a proper fraction. Remember, a proper fraction is a number that's between 0 and 1. That's why the numerator is smaller than the denominator. You agree that 1/3 is between 0 and 1? Okay? Is 5/4 a proper fraction? No. That's what kind of fraction? Improper. So a number bigger than 1, bigger than or equal to 1, is an improper fraction. So this right here is what kind of, your base is what kind of fraction? Improper. Because that's 3 over 1, right? So if your base is a number bigger than 1, your graph's going to do what? Increase. All right, so let's go and write this down. So since I'm going to go back and do it over here. Here. So since, write this right here. Since, I'm going back to this problem we did earlier. Since the base, which is 3, is greater than 1, f of x, which equals 3 to the x minus 5, is an increasing function. Which means the y values keeps doing what? The y values keep doing what? Not decrease. Oh, increase, right. They increase. It gets bigger and bigger, right? It kind of makes sense because when I raise 3 to the second power, 3 to the third power, 3 to the fourth power, what's happening when x gets bigger? Come on, guys. When x gets bigger, what happens to 3 to the x? It gets bigger. So my y value increases. So that's the increasing function. Whereas over here, when I keep raising 1/3 to a bigger power, what's happening to this fraction? It gets smaller. It gets smaller because watch what I'm talking about. 1/3 to the first power is what? 1/3. 1/3 to the second power is 1/9. 1/3 to the third power is 1 over 27. What's happening to these fractions? They're getting smaller and smaller and smaller. So that's what's happening here. When you go back to this graph, see your y values, as x gets bigger and bigger and bigger, your y values are getting what? Smaller, smaller, and smaller. Right? So that's why when the base is proper, your y values get smaller, whereas if it's improper, they get bigger. Okay? All right, so over here, it says the base is 3, which is bigger than 1. This is going to be an increasing function. For the one we just did, since the base is 1/3, and remember, in an exponential function, your base must be bigger than 0, correct? Your base can never be negative, and it can never be 1 either. So I'm going to write this. Since the base is 1/3, which is between 0 and 1, f of x is decreasing. So all of this helps you to draw an exponential function. All of that helps. All right, let's talk about the domain of what we just drew. What's the domain of the one that we just did? All real numbers. Domain's all real numbers. So you're going to say domain, -infinity to infinity. But the range is not all real numbers. Okay, so let's talk about the range. Here's the graph again. You go along the y-axis from bottom up. I start touching the graph at that horizontal asymptote, which is what? Okay, so think about the points of this graph, though. Is the points of this graph are getting closer and closer to what? -5 without actually becoming -5, correct? So it gets closer and closer to it. So I'm gonna use -5, but I have to use what with -5? Huh? Parentheses. You're going from -5 all the way to what? Infinity. So your range is from -5, because that's your horizontal asymptote, -5 all the way to infinity. So that's your range. So it's very simple to graph these exponential functions. Once you find your horizontal asymptote, and once you know whether it's above or below, you plot 3 points, and then you connect them. It'll be that number. Right. It'll be the number. Yes. Yep. When you did transformations for section 2.5, you had some vertical transformation that went up. You had some that went down. Remember that? Like x squared plus 5, x squared minus 5. All right, suppose we had this. -3 to the x plus 2. -3 to the x plus 2. All right, so what is the horizontal asymptote? Okay, don't say 2 though. You gotta say, huh? Y equals 2. Okay, y equals 2. And is the graph above or below the horizontal asymptote? It's below because of that negative. That's a reflection. Okay, so this is a reflection about the horizontal asymptote. All right, so a reflection about the horizontal asymptote. So you can see how it's going to look. Okay, so we're going to use a t-table. And so let's go ahead and plot the graph the horizontal asymptote. So the horizontal asymptote is y equals 2. So I always do that first. Y equals 2 is here. Okay, this is y equals 2. And I know that my graph's going to be located where? Below it. Okay, so what would be a nice number to use for x? 0. That's going to be your y-intercept. Okay, y-intercept. Okay, now if that negative wasn't there, would you think about this for a moment? If the negative wasn't there, would this function be increasing or decreasing? If the negative wasn't there, it would be increasing because your base is 3. But the negative is a reflection, so instead of increasing when reflected, it does what? Decrease. Very good. It's actually decreasing because of the reflection. All right, so let's just look at this. So the y-intercept, you're going to say y equals -3 to the 0 plus 2. Now be careful when you do this. You got to say 3 to the 0 first, because that's what's being raised to the 0 power, not -3, 3 only. So what's 3 to the 0? And this becomes a -1. And what's -1 plus 2? 1. So I'll plot the point 0, 1. Okay, 0, 1. So that's here. See it? Okay. And so, all right. So I want you to think about this for a moment as we go through this. So we're going to pick 2 or 3 more points, but I want you to think about this. You know your graph is going to decrease, right? Make sure you understand that. If that negative wasn't there, it would be located above the horizontal axis. It's going to be doing what? Increasing. Since I'm reflecting it, it's going to do what? Decrease. So you understand, even without plotting any points, that what's going to happen on the left of this is going to go towards the horizontal axis. So all you got to do is give me 3 more points on this side then. Or 2 more points, actually. 2 more points, because you already found 1. So let x be what? 1. You see what I did? Think of it like that. So on this side, since I know that it's going to decrease, this part's going to go towards the horizontal asymptote. Right. So if x is 1, I get y equals negative 3 to the first power plus 2. Now be careful. You're not saying, well, it's okay. Even if you made a mistake, it wouldn't matter. 3 to the first is what? 3, and this is still a negative 3. What's negative 3 plus 2? Negative 1. So I plot this point 1, negative 1. So 1, negative 1 is here. And I just need one more. So let's say x is 2. X is 2. I get y equals negative 3 squared plus 2. Now, this way you need to be careful. Don't say negative 3 squared is 9. That's not true. That is not a 9. And even if you did, you should realize you did something wrong, because if you said negative 3 squared is 9, and 9 plus 2 is 11, and you go and you plot 211, what do you notice? It's way up here, and you know your graph's supposed to be located where? Below. So you know you did something wrong. Okay? It doesn't make any sense. So you got to remember that since there's no parentheses, what is being raised to the second power? 3 only. So what's 3 squared? And this becomes a negative 9. And negative 9 plus 2 is a negative 7. And you're done. You just plot that point to negative 7. You connect the dots with a graph. I could do this a little better. And you get something that looks like this. Okay, so there's your graph. All right. Now, what's the domain? Oh, first of all, you see that's decreasing, correct? Okay. Now, make sure you understand. I know a while ago I said if the base is bigger than 1, it's increasing, and now we're saying it's decreasing. It's decreasing only because of the what? That reflection out here. So instead of being above the above the horizontal asymptote, increasing, is being reflected above the horizontal asymptote, decreasing. Okay. All right. So f of x is an decreasing function, a decreasing function. What's the domain? Real numbers, always. Okay, now let's talk about the range. Okay, so the range. So I'm going to go here. I'm going to put the graph back up. What do you think the range is? Negative infinity to what? 2 with a parentheses. Very good. Because my graph never is 2, but it does get close and close to what? 2. So 1.99, 1.9999, and so on, without actually equaling 2. So my range will be negative infinity to 2 parentheses. Okay, and that's all that is. All right, let's talk about a different base. Let's talk about a different base. Now, there's a base that's an irrational number. Now, all these bases here, when we looked at all these bases, 3, 2, 1/3, 1/4, whatever it may be, those are rational numbers. Those are rational numbers. Remember in high school geometry, you dealt with an irrational number called pi? In high school geometry, you dealt with an irrational number called pi. Well, there's an irrational number that's used quite often with exponentials, and that's the number e. The number e. Now, in one of your videos, there's an explanation of where e comes from. So when you watch the video, it's in there. But on your calculator, you will see an E button. See up here, right here, right? See where it says e to the x? Yes, right above the LN button. It's the blue one. You see it? Okay. I can't. There's. All right. Do y'all see it on yours? Okay. All right. Okay, so before we start graphing those bases, let's just use a calculator and approximate what some functions of e raised to power is. So let's just evaluate these. Okay, first of all, let's figure out what E is, though. So let's evaluate just the number E. Okay, just the number E. All right. So the exponent is understood to be what here? 1. So the exponent is understood to be a 1. So I'm going to approximate, because that's an irrational number. E is an irrational number, just like pi was an irrational number. Remember pi, we approximate pi to 3.14. Remember that? Okay, but pi itself is an irrational number because these digits, they keep on going, they never repeat, there's no repetition at all. So that's why it's called an irrational number. A decimal 1.333 repeating like that, is that rational or irrational? That's rational. That's a rational number. 3.14 and so on, that is an irrational number because there's no repetition at all in any of the digits. This is rational because I can write this as 1 1/3, which is what fraction? 4/3? There's no way you can write pi as a fraction, an integer divided by an integer. So that's why it's called an irrational number. The same thing with E. There's no way you can write E as a rational number. But when you look at your calculator, what E is, so you're going to say, when you punch into your calculator, you're going to do second first, so click on second, and then press that LN button. And you see that E to the X shows up, see it? E to a power, see? Okay. And then you're going to type in 1, so type in 1, and then close it. So you see I'm trying to find E to the first power. Press equal, and E is approximately equal to 2.718 to 3 decimal places, 2.718. See, there's no repetition. There's no repetition. Now don't say, well, this looks like it's repeating 8281, 828, but that digit right here is not necessarily 1. Okay, so there really is, it's not a rational number. There is no repetition. If you had a calculator that went on further, you would see that there are no set of digits that keeps repeating. It kind of looks like it, but it's not. It's not though, because you don't see what these are. Okay, so it's not 1828, 1828, 1828. Yeah, I know. Okay. All right, so it's an irrational number. Okay. So we approximated though. When in some of your science courses, your physical science courses, you would approximate it as 2.72 usually. So you would say 2.72 to 2 decimal places, or you could say 2.718. So that's what pi is approximately equal to. I'm sorry, excuse me, E. Well, that means approximation. If you said E equals 2, I would hope you know that you did make a little error there. I wouldn't take off, but when you say if you say E equals versus E is approximately equal to, those are two different things. E equals means an exact number. An approximation means something that's rounded off. I've rounded these off, so that's an approximation. All right, what about the next one? Try E squared. And go ahead and use 3 decimal places. So on your calculator, you're gonna punch in what first? Second, then the LN button, and then type in 2, close it, and that's about 7 point. Okay, to 2 decimal places, 7.39. Okay. All right. What about E to the 1.2 power? All right, so E to 1.2, so second, Ln 1.2, you'll get 3.32. Make sure you get it on your calculator. Okay? All right, 4. Now, E to the square root of 5. e to the square root of 5. So you can type in second ln, right? Second ln. Then you're going to type in the square root. So square root, I got to type in second square root again. See how it looks? You do that second function twice. Now, what do I type in next here? 5. What do I do? Close that square root, and then I got to close the exponent. Yep. See how it looks? So you have to say second e, and then to get the square root, you got to say second x squared, and that gives you that. And then close both of those. See those open parentheses? You got to close them. Then press equal. Did y'all get this? 9.36. 9.36. Make sure you see that. What about e to the negative square root of 7? So let's do another square root, except this time it's negative. So what do I type in first? Okay, so you get second, and then what do I type in next? No, you're going to say e to that x, right? All right, and when you do that, it kind of opens up some stuff here. What you do the exponent, what's the exponent? Square root, right? Oops, you're right. Yep. Do what next? The negative, and then what? Square root, and then type in what? Now when you do the square root, it puts a parentheses there, right? What do I type in next? Then what do I do? Close, close, and then enter. So your calculator is going to look like this. So you're going to say second. Oops, wrong one. Second. Looks like this, right? Then I got to do the negative. Negative square root. So what do I press next? Second again with a x squared or that square root. What do I type in? 7. Close, close, and then press equal. So 0.07, is that right? Yes or no? Yes. All right. Now you knew it wasn't supposed to be negative. You might say, well, I had a negative exponent. Why isn't it negative? Well, why isn't it negative? That's not why. What kind of number is your base? A positive. A positive number raised to any power is always what? Positive. That's why. You were way off with that, girlfriend. So a positive number raised to any power is positive. Okay? All right, now let's do the graph of one of these. So let's graph f of x equal e to the x. Let's do e to the x first. Let's just do that one. All right, what is the horizontal asymptote? Okay, 0 or y equal what? 0. So the horizontal asymptote is y equals 0 because that's what it is, right? Plus 0, y equals 0. So a horizontal asymptote is y equals 0. Oh, by the way, I forgot to mention this when we talked about it. The base E is called the natural base. N-A-T-U-R-A-L, natural base. Okay, so base E is called the natural base. So in my math lab, they may ask you some words like this. What is E called? E is called the natural base. All right, so natural is base E. Natural base is base E. Okay, now, so y equals 0. What's another word for y equals 0 in terms of this plane? Not the origin. Huh? Not the x-intercept, the x-axis. X-axis. Y equals 0 is the x-axis. Y equals 0 is the x-axis. Kind of makes sense, right? Because this is y equal 1, correct? That I'm showing you. Isn't that y equal 1? This is y equal what? 2. This is y equal 3. This is y equal 0, which is also the what? X-axis. Don't say origin. X-axis. Origin is a point. Y equals 0 is not a point. Y equals 0 is a line. Okay, there's a difference between the two. So R x-axis. Okay, so I drew my dotted line, so y equals 0. All right, now is the graph above or below the horizontal asymptote? It's above. All right, so let's plot some points. Let's use the t-table. What's an easy one to use for x? 0, because when you use 0 for x, you are finding the y-intercept. And an exponential function always has a y-intercept. So you're going to say y equals e to the 0 power. What's e to the 0? 1. So I'll plot the point 0, 1. Now I'm going to ask you this next question. Is this an increasing or a decreasing function? Who says it's decreasing? Who thinks it's decreasing? Or who doesn't know? Well, we talked about the base. What is the base here? No. They're all positive. 1/3 was positive. Bigger than 1. E is approximately equal to 2.72, correct? That's not bigger than 1. So if it's bigger than 1, your function is doing what? Increasing. So in your mind, you're thinking this. Right? So you can tell me right away what happens to the left of this y-intercept. It goes towards the horizontal asymptote. And all you got to do is give me 2 more points that's on here to show me that it's rising rapidly. All right, so remember our discussion about increasing or decreasing based on the base. If the base is bigger than 1, your function is increasing. If your base is between 0 and 1, it decreases. Now, there's a reflection. It kind of changes stuff, but there's no reflection here. So all I got to do is pick 2 more points that's on this side. So give me another number for x. What would be a nice one to use? 1. So if x is 1, I got y equals e to the first power, which we know is about what? 2.72. So 1, 2.72. So we just kind of approximate where that is. It's not going to be on an intersection of those grid lines. This will be an approximation that we're going to be doing. So 1, 2.72 is close to 3? Yes or no? You guys can put it here. All right, close to 3. Again, I need one more number for x. Give me another number for x. 2. So I get y equals e squared. What's that approximately equal to? On your calculator, you'll get 7 what? 7.39. Y'all agree? So 7.39 is close to 7.5, so about in the middle. And there's connect them and you're done. There's your graph. That's all you have to do. Okay? That's all you have to do. That's what an exponential function looks like. Now, so we know that f of x is increasing, correct? We also know the domain. What's the domain? So negative infinity to infinity. Now let's talk about the range. The range. What do you think the range is? -1 to infinity? 0 to infinity. Correct? 0 to infinity. So from 0 to infinity. Okay. All right. Let's do another one. So let's graph f of x equal e to the x minus 6. E to the x minus 6. Okay, what's a horizontal asymptote? Always do that first. What's a horizontal asymptote? -6. Y equals -6. That's correct. Okay. All right, so I graph that y-intercept, the horizontal asymptote. So y equals -6 down here, right? So the dotted line like this, and this is y equals -6. Is the graph above or below that? It's above because there's no reflection, correct? All right, so let's use the t-table. Oh, and is the graph increasing or decreasing? It's increasing, so f of x is increasing. So once I find the y-intercept, then it kind of helps me to see which points to use for x. So I'm going to let x equals 0, so that's your y-intercept. And so when x is 0, I get y equals e to the 0 minus 6. What's e to the 0? And so what's 1 minus 6? Okay, so I plot the point 0, -5. And notice what happens when I plot the point 0, -5. Here is 0, -5. You could tell me which side of this is my graph going towards the horizontal asymptote. The left side. Because this was what kind of function? Increasing. That was an increasing function. So on this side, you know it does this. Okay? Now give me another number for x. 1. X is 1. I got y equals e to the first minus 6. Okay, use your calculator. So in your calculator, you're going to say e to the first minus 6. So you do this in your calculator, though. You're going to say second. E, you're going to say to the first, close that, though, and then subtract what? 6, and then press equal, and you get about -3.28. Make sure you got that -3.28. So -3.28. All right, so I plot that point. So that's an approximation. So 1, -3.28. 1, -3.28 is close to -3. It's about here. Okay, I need one more. Give me another number for x. 2. So I get y equals e squared minus 6. So in your calculator, say e squared minus 6. E squared minus 6 is second. E to the x. So I say e squared, subtract 6. So -1 point, no, positive, right? Positive 1.39. Positive 1.39. And you plot that point. 2, positive 1.39 is about here. And just connect them and you're done. This is it. That's what you get. All right. What's the domain? All real numbers. So domain's all real numbers. So put domain all real numbers. What's the range? Negative what? 6. Okay. -6 to infinity, correct? All right. So any questions on that? All right. So that's basically those. Oops. Okay. 2 of those worksheets you can do. All right. Worksheets 1 and 2 you can do. Now worksheet 3 has to do with some formulas. I'll give you the formulas. So let's talk about worksheet 3. So this is for worksheet 3. Part 3, yes. So section 4.1, part 3. Okay, so there are a couple of common formulas that you can use for compound interest. So there's this formula. So this will be your compound interest formula. And there are 2 of them. I'll give them to you. You don't have to memorize them, just know when and how to use them. So the first one is this one. A equals P times, in parentheses, 1 plus R over N, and that stuff that's inside this parentheses is being raised to a power, and that power is NT. There's another compound interest formula, number 2, which is just this. A equals P times E, and remember we just talked about E, that natural base, to the RT. So the exponent of E is RT. Huh? What? No, you're about to use them though. So P stands for the principal, like the amount of money you invest, the initial amount. So P is the principal, the initial amount of the investment. So if you say you invested $8,000, then P is going to be what? $8,000. R is the interest rate. And it must be as a decimal. So if your interest rate, let's say, is 4%, then you're going to say R equals what? How do you remember 3 semesters ago, that whole chapter in percents? You moved the decimal point 2 places to the left. So 4% is 0.04. So that's how you would write R. You don't put 4, you would put what? 0.04. So R must be written as a percent. As a decimal. T is your time in years. T is the time in years. Okay? So if they tell you that you're only going to do this for 6 months, so if it's in months, you must convert that to what? Years. And how do you convert months to years? Divide by 12. To convert months to years, you divide by 12. So 6 months is 6 divided by 12, which is what? 1/2 of a year? All right. But most of the time it will be written in years. Just once in a while, though, they'll give you the time in months. You got to convert it to what? Years. And convert months to years. So this is 18 months. How do you convert that to years? You divide by what? 12. So you say 18 divided by 12. That's how you convert months to years. And N is the number of times the interest is compounded per year. So N is the number of times the interest is compounded per year. So interest is earning interest. So interest is earning interest. So this is not simple interest. This is compound interest. So if you're told that it's being compounded, so listen carefully to this, compounded semi-annually. So if you're told it's being compounded semi-annually means how many times a year? 2. So N would be 2. So you would let N be 2. Huh? So if it's being compounded, so the word says it's being compounded monthly, then N equals what? 12. Because there are 12 months in a year. If it's being compounded quarterly, how many quarters are there in a year? 4. And that's about all that you really need for the compounded part. So compounded semi-annually, you're going to let N be 2. So the word says compounded monthly, you're going to let N be 12. Compounded quarterly, you're going to N be 4. Okay? Now that's all for this first formula. That's all for this one. Now, and A stands for the amount you end up with. So A is the amount you end up with. Now, A is the same thing as this A, P is the same thing as this P, R is the same thing as this R, and T is the same thing as this T. Is that clear? Okay. Now you may say, well, when do I use this one? Now notice what's missing. What letter is missing in here? N. So if it no, it's not going to say that. If it says it's being compounded continuously, continuous means an infinite number of times. Compounded continuously, then that's the one you're going to use. You're going to use the PERT formula. PERT. All right. So if it's being compounded a finite number of times, see finite versus infinite. Finite I can count. Compounded semi-annually, I can count. How many times is that? 2. Compounded monthly, I can count. How many times is that? 12. Compounded quarterly, I can count. How many times is that? 4. Compounded continuously, that's an infinite number of times. I can't count that. So you're going to use this formula. All right? So it's very simple to use. What you need?
I'll message you about what's going on with me. But I need to answer.
Okay.
All right. What do I tell you?
That table that's next to right there. Okay, so if you so let's suppose you invest $6,000 for 7 years. So $6,000 for 7 years at a rate of 6.5%. How much will the investment be worth if the interest is A, compounded quarterly? All right, so you invest $6,000 for 7 years at a rate of 6.5%. How much will the investment be worth if the interest is compounded quarterly? So every 4 months, every 3 months, the interest is earning interest. Okay? Huh? Yeah, that's hypothetically though. I made that up. It's not going to happen. All right. So, what form are you going to use? The first one. So you're going to write it down. It's A equals B times 1 plus R over N raised to NT. Okay. So, what letter am I looking for? A. So A equals P. P is your initial amount. The initial amount. What was the initial amount? 6,000. So you say 6,000 times 1 plus R. What's R as a decimal? Y'all agree it's 0.065? Okay. 0.065. Divided by N. What's N? 4. Because quarterly, right? All raised to, and put that in parentheses. Put the NT in parentheses. What's N? 4. What's the time? 7? Okay. Now let's use a calculator. So on your calculator, just write it, just type in what you see. Type in what you see. So you say 6,000, and then open parentheses. And then what do I type next? 1 plus 0.0065, is that correct? Divide by 4. What do I type in next? Parentheses. What do I do next? Raised to. So that's this caret right here. All right. And then what do I type in next? Okay. Now you could say 28, right? But sometimes, so you wouldn't need parentheses if you just say 28. But sometimes one of these is a decimal. So I would if it's a decimal, I'd leave it as I'll put them in parentheses. times 3 parentheses. You say parentheses, what do we say? 4 times 7 and then close, and then press equal. And so that's about 9,000 to the nearest cent. To the nearest cent. Nearest cent means what decimal place? The hundredths decimal place. The hundredths decimal place. So $9,422.50 what? 2 cents. Yes. Yeah. Yeah. Make sure that's what you got. Make sure on your calculator this is what you end up with. $9,422.52. Make sure that's what you ended up with. Well, yeah, but that's not. No, not at 6.5%. Okay. All right. Okay. Is there any question on that? You say this. You say 6,000. Parentheses 1 plus 0.065 divide by 4, close the parentheses, then you raise it to a power. You got to press this to raise it to a power. That's your power. And then open parentheses, 4 times 7, close, and then press equal. Make sure that's what you got. Okay? Make sure that's what you got. Any questions? All right, now, so that part's easy. Doing this kind's easy. So in worksheet 4.1 part 3, I think you can do only one part on that. The continuous one, we'll do another one like this. We'll do, the next one will be compounded monthly. Then we'll do one where it's compounded continuously. If it's compounded continuously, you got to use the other one, right? So we'll do that next class period. And then we're going to start looking at logarithms. Then we're going to look at logarithms. All right, now, as much as we can.